Welcome to the Deep Dive, where we dig into fascinating research and pull out the insights that matter, and maybe have a little fun doing it.
Looking forward to it.
So today we're tackling something, well, fundamental, walking upright.
Something we barely think about.
Exactly. But getting here to just walking around on two legs, it took a massive evolutionary redesign. Our bipedal stance is actually pretty weird compared to our ape relative.
Definitely weird, and the pelvis is right at the heart of that weirdness.
That's our focus today, the pelvis. You sent over some incredible sources, including that big Harvard study in Nature.
Yeah, it really sheds new light on things.
So our mission is to unpack how our pelvis got its unique shape. We're talking two major steps, the genes involved, a whole evolutionary makeover.
It's a great story of evolutionary engineering, really. A compromise written in bone.
Okay, so let's start there. Why is the pelvis called the keystone? What makes it so central?
Well, it's the connection point, right, between the spine and the legs. But more than that, it's the bone that changed most dramatically in our lower body to make bipedalism work.
More than the legs or feet.
Arguably, yes. The changes are profound. Millions of years of tweaking, or rather, fundamental redesigning. It wasn't just minor adjustments.
Okay, so paint that picture for us. How different are we talking? Ape pelvis versus human pelvis.
Night and day, almost.
Yeah.
Think about chimps, gorillas. Their upper hip bones, the ilia, they're tall, narrow.
Tall and narrow.
Yeah, and they face mostly front to back, like thin blades if you look from the side.
Okay, blades. What's the advantage of that shape for them?
It's perfect for anchoring the huge muscles they need for climbing. Powerful leg movements, hip extension, great for life in the trees, or moving fast on all fours. Think vertical power.
Vertical power, got it. So they have these blade-like structures. How did ours end up so different?
Ours rotated, the hip bones rotated outwards to the sides. They flared out.
Creating that bowl shape?
Exactly, creating that distinctive bowl or basin shape. You know, the word pelvis even comes from the Latin for basin.
Ha, that fits perfectly. And that bowl shape isn't just for looks, right?
It's not at all. It's crucial. It provides the attachment points for the muscles we need to balance when we shift our weight from leg to leg. Walking, running, it wouldn't work without it.
So it gives us stability.
Stability, support for our organs against gravity, and the leverage for our gluteal muscles. Those muscles are key for keeping us upright. It's a completely different structural approach.
A wide, sturdy base instead of their tall, narrow one.
Pretty much. Built for a different world, a different way of moving.
Okay, so anatomists knew our pelvis was unique. But the how? The actual evolutionary steps. That was the mystery.
That was the big question, yeah. We saw the end result, but the developmental path, the genetic tweaks, largely unknown until this recent work.
And this Harvard study started to crack that.
It really did. They found these two major mechanistic shifts, changes in how the ilium develops in the embryo, totally different from other primates.
Okay, mechanistic shifts. Sounds important. Let's break down the first one.
Right, step one. It starts with understanding how most long bones grow.
Okay.
Usually, you have cartilage cells on growth plates, and these plates line up along the main axis of the bone, head to tail, adding length, like building a tower, stacking bricks upwards.
Makes sense. Standard procedure for getting longer bones. So what's the twist with our ilium?
Here's the amazing part. Early on, in human embryos, the iliac growth plate does start out like that, head to tail alignment, normal.
Okay, starts normal.
But then, around day 53 of gestation.
That's really early.
Incredibly early. The growth plates radically shift. They rotate perpendicularly, 90 degrees from that original axis.
Whoa, a 90-degree flip, just like that.
Just like that. It's not a gradual change. It's a fundamental reorientation.
So the whole direction of growth changes in an instant, developmentally speaking.
Exactly. And the immediate result of that single flip, it makes the hip bone short and wide instead of tall and narrow, all at once.
Not short then wide, but short and wide simultaneously because the growth direction changed.
Precisely. It was apparently quite a surprise even for the researchers. Such a clean, dramatic shift so early on. A really efficient evolutionary hack, if you will.
That is wild. A 90-degree flip rewrites our hips. What's making that happen? Genetically.
They dug into that too, identified over 300 genes involved, but two really stood out, kind of the master architects of this flip.
Okay, who are the stars?
SOX9 and PTH1R. Those two seem to have outsized roles, as the study put it.
SOX9 and PTH1R. And I guess we see how vital they are when things go wrong.
Tragically, yes. There are human genetic disorders linked to mutations in these genes.
Like what?
Well, a mutation in SOX9 causes something called campomelic dysplasia. The hip bones end up abnormally narrow. They don't have that sideways flare.
So they look more like the ancestral non-human shape.
In that aspect, yes. And mutations in PTH1R also lead to abnormally narrow hip bones, among other skeletal issues. It really highlights that these specific genes are absolutely critical for building our unique human pelvis shape.
It's like a direct line from the gene function to the bipedal adaptation. Okay, so this first major step, the 90-degree flip driven by SOX9 and PTH1R, when did this likely happen in our past?
The thinking is this started right around the time our lineage split off from the other African apes.
So we're talking 8 million years ago? Somewhere in that ballpark.
Exactly, that deep in our evolutionary history, a really foundational change.
But that was just step one, you said. There's another layer to this.
Yes, step 2. Equally important, and it deals with when and how the cartilage actually hardens into bone. Ossification.
Right, ossification. So how does that normally work in, say, our leg bones?
Typically, ossification starts in the middle of the bone shaft at a primary center, and it spreads outwards, but also rapidly invades the inside of the bone, hardening from the core.
Okay, inside-out hardening. Standard stuff.
But not in the human ilium.
Of course not. What's different there?
Well, when iliac ossification starts, around day 57, it begins near the back, near the sacrum, and it spreads out radially.
Okay.
But, and this is the key, the mineralization stays restricted to the outside layer, like it forms a shell first.
So it's hardening on the surface, but the inside stays cartilage.
For a while, yes. The ossification of the interior, the deep internal hardening, is delayed by about 16 weeks. It only really starts to fill in around week 24 of gestation.
16 weeks? That's a huge delay. Why? What's the point of keeping the inside softer for so long?
It allows the bone to keep growing and achieve that complex flared basin shape before it gets locked down internally. If it hardened quickly inside out, it might constrain that shape development.
Ah, so the delay facilitates the final shaping. It needs to stay pliable longer to get that curve right.
That seems to be the idea. It lets the bone achieve its intricate geometry, essential for bipedalism, and potentially for something else too.
Before we get to that, are there key genes for this delayed timing as well?
Yes, they identified regulators for this pattern too. Genes like RUNX2 and FOXP12 seem to be the conductors for this specific ossification timing.
RUNX2, FOXP12. Okay. Now, you mentioned another reason for this delay. This happened later, right? Maybe the last couple of million years.
That's the estimate, yes. Much later than the initial 90-degree flip. And it ties into a classic evolutionary puzzle, the obstetrical dilemma.
Right. The conflict between narrow hips for efficient walking and wide hips for childbirth.
Exactly. We need narrow hips for locomotion, but human babies have increasingly large heads. It's a trade-off.
So how does the delayed ossification help with that?
By keeping the pelvis development slightly more flexible or adaptable for longer, it might have been a key factor in allowing our species to strike a balance. To evolve a pelvis that was good enough for walking efficiently, but also just wide enough, or perhaps shaped in such a way, to allow for the birth of big-brained infants. It's evolution finding a compromise.
That makes so much sense. It's not just about walking, it's about reproduction too, a dual-purpose adaptation.
Absolutely. And these developmental changes translate directly to function. The study points out how key walking muscles, like gluteus medius and minimus, attach very early to this developing cartilage structure.
So the muscles are ready and waiting to hook onto this newly shaped bone.
Pretty much. Even the rectus femoris muscle attaches early to a feature called the AIS, the anterior inferior iliac spine, which is a specific hominin trait important for hip movements and upright walking. The muscles and bones developed hand in hand.
And we can actually track this progression in fossils.
You can see hints of it. Ardipithecus, around 4.4 million years ago, shows some early human-like pelvic features.
Already.
And then Lucy, Australopithecus afarensis, at 3.2 million years ago, shows more developed bipedal traits. You see more of that flaring of the hip blades, suggesting the muscles for balancing were becoming more important.
So the fossils line up with this story of gradual but profound change driven by these developmental shifts.
They seem to, yeah. It provides a potential mechanism for what we observe in the fossil record.
You mentioned one of the researchers, Cappellini, suggested this changes how we should think about human evolution overall.
Yes, his point was quite profound, I thought. He said we shouldn't view later changes, like the big increase in brain size, using a chimp-like developmental model. Meaning the groundwork for accommodating those bigger brains, the redesigned pelvis, was already being laid millions of years earlier. The pelvic changes came first, creating the context for later brain expansion.
So the foundation changed before the rest of the building went up, so to speak.
Exactly. It forces us to rethink the sequence and interdependence of these major evolutionary events.
And it wasn't just one magic gene for the flip and one for the delay, right? You said hundreds were involved.
Oh yeah, definitely not simple. They found hundreds of regulatory sequences active in specific cells. It points to a complex, polygenic process.
Polygenic, many genes working together.
Right. Hierarchical interactions between genes like SOX9, PTH1R, RUNX2, FOXP12, and others. It was complex selection, acting on many targets over a long time to fine-tune the whole system. It wasn't one lucky break. It was a long, slow sculpt.
Wow. Okay, so let's recap for everyone listening. We've seen these two incredible innovations. First, that early, dramatic 90-degree flip in the growth plate, making our hips wide.
Driven by genes like SOX9 and PTH1R, starting maybe 5–8 million years ago.
And second, that much later delay in internal bone hardening, allowing the complex bowl shape to fully form.
Orchestrated by genes like RUNX2 and FOXP12, likely helping resolve the obstetrical dilemma in the last couple of million years.
These tiny changes, deep in embryonic development, fundamentally reshaped us and made us human.
It's the microscopic foundation for our macroscopic way of life.
So here's something to think about. The way you walk, stand, even the possibility of human birth, it all hinges on these ancient embryonic tweaks, these evolutionary compromises encoded in your genes.
Compromise is still playing out today.
Right. Our pelvis isn't just static bone. It's an archive of evolutionary negotiation. So, what other parts of you, things you take for granted, are the result of similar ancient trade-offs? What biological deals are your genes still negotiating right now?
Makes you wonder what stories are hidden in other parts of our anatomy.
Definitely. This dive into the pelvis shows just how much ancient history we carry within us. Thanks for joining us on the deep dive.
My pleasure.